topic of our presentation of our project is recovering 3D human pose using game engine generated dataset. And we want to compare results achieved by models trained on our dataset and on standard datasets. Firstly, let's introduce what problem of pose estimation exactly is. We can distinguish two types of pose estimation: 2D pose estimation and 3D pose estimation. 2D, it's basically when you have an image and you want to find coordinates of to the pixels of key points of the character visible on the screen. And 3D pose estimation, it's a task when you have image of character 2, but you want to predict 3D pose, 3D coordinates of character in some world coordinate system. Well, why is it important? Because it's easier to have training data set for 2D pose estimation, because you can take some images and delegate task to create annotations to some people, because it's the only problem is to mark key points like elbow, like feet, like head. In 3D pose estimation, this problem is much harder, because is very difficult, maybe impossible, to have 3D coordinates, because it's very hard to mark the third dimension. And we can address this problem, for example, in that way that you have mockup studio, and then you can find some actors to find some actors and ask them to make some poses. But dataset generated in that way may have some problems, like not a very high variety of created poses and characters. And our main goal is to create synthetic and artificial datasets and compare their performance. In a synthetic dataset, we can introduce bigger variety of character appearances, clothes, and locations. Our approach is we want to combine data created in Unreal Engine with some realistic data set from internet. And our main goal is to investigate how the increased diversity of our synthetic dataset impacts the model performance compared to human 3.6 dataset. And if about evaluation, all experiments will be conducted using the same model architecture based on BlazePose. Unreal Engine is widely used game engine, and we are able to achieve the very realistic looking locations and characters. We want to take from MetaHuman. This is a web service related with Unreal Engine ecosystem with Epic Games that allows creating realistic looking characters with different clothes and skin colors. Okay, let's introduce our model architecture. Okay, on the left on the right, we can see the scheme of this model. This architecture was reverse engineered from files provided by Google in MediaPipe, but the final reconstruction architecture is different to architecture described in Blaise Paul's paper. We reconstructed two versions of this model, heavy and medium, but first preliminary experiments showed that medium versions achieve worse result, and we decided to focus on heavy architecture. Each block consists of some simple layers like convolutions, ReLU, deepways convolutions, and each block is composed into block sets. These block sets are visible in the middle of the diagram. Here we can see decoder blocks and regression blocks. Decoder blocks have two inputs. One is the standard input, and one is skip connections marked in dot lines. The main difference between heavy and light architecture is that in the light architecture, creators removed some skip connections between heatmap head and regression head, and what is more, in medium architecture there was no connection between the output of left head of this model and regression head. In theory, theoretically, it should provide the higher speed, but it can increase. It can be related with decreasing of accuracy.
Okay. So for the dataset part, we used Unreal Engine to generate the datasets, the synthetic and our dataset in particular. So we wanted to compare how our datasets compare to the model trained on only the human 3.6M images, the original ones, not any sort of argumentation. So in the case of our synthetic datasets, I started out by recreating a similar room to the one where the human 3.6M should take place. And I would say that it is somehow similar. We also used two time settings in Unreal Engine to show that making those shots in a game engine can improve the amount of data we can generate. And the poses have been mapped from the 3D position data and X-maps provided with the human 3.6M dataset. So as we can see, the synthetic dataset is somehow similar to the human 3.6M dataset, but we also made some other locations using 3D scans of various locations, and that is our dataset. It is not using any human 3.6M data, it is only using random motion data from XAML and 3D scanned locations. Okay, so the results are here. So first of all, we can see that the model trained on the human 3.6M dataset and our synthetic model don't really perform that well on each other dataset. However, what is interesting is that if we train a model on both the human 3.6M dataset and the synthetic dataset, the resulting model performs, of course, both good on both of the datasets, suggesting that they are compatible. However, we also can see that this synthetic model also performs much better than the other models on our dataset and on MPII. Okay. We also can see that this model trained on our dataset also performs okay-ish on, performs somehow on those two human 3.6M dataset and synthetic datasets. However, from this we can see that there is value in combining both a real and synthetic dataset, and that just generating one with this approach might not be enough. So I think that's all.
So I think that it's worth adding that we showed that mixing realistic human 3.6 dataset with our artificial data causes in increasing the quality of predictions in terms of these losses. And I think that it's a good point for some future work that we can that it could be done that we can change a bit our model to be able to have as an input views from two cameras, because if model have only one view, some points may not be visible, and it's obvious that model can't predict it correctly. Having views from two perspectives can solve this problem, and due to the fact we have artificially generated dataset, we can generate very many images from different cameras from different angles, and it's possible to it could be possible to verify whether adding some additional losses like mask losses. Mask, I mean the white pixels when the character is present. It allows us to create better prediction. And the next point more, creating dataset in artificial way allows, in theory, to predict more things, not only coordinates of points, but it allows to predict, for example, bones rotations that are useful to create some retargeting and using model trained in that way in some commercials. And I think that's all.
I will only say that the most interesting scores are from MPAI because it's another publicly known dataset that is used for evaluating poses. However, it's only 2D. It doesn't have 3D data. So this is, I think, the most interesting part of these results. So I think that's all.
So do you have any questions? So I have one. So maybe I haven't got that, but can you tell us, because M0 is model, right?
Yeah, so basically we have 4 models to train it on different datasets. So the numbers are just our code names for those models, basically.
Okay, and so synthetic is your dataset, right?
Yes, so as you can see on this slide, so synthetic looks like this. So this is like this remodeled room based on what I could get from those images from the human 3.6M. It's like manually modeled, it's not like something automatic. And this our dataset doesn't, okay, and in synthetic dataset, we are using motion data from human 3.6M. However, in our dataset, which is another synthetic dataset, it is using 3D room scans, not this 3D model of this room, and it is using different motion data than human 3.6M.
So maybe this is what I didn't get, because you have this data, like original dataset, your dataset, and synthetic dataset, right?
Basically, yes. Original is this human 3.6M.
Which one is which in this table?
So yeah, this is the original one. This is the synthetic one, and this is our one. This is our.
And this metric is what?
This is loss, which is calculated as the average MSE loss, I think, for 2D and 3D. Because for heat map, it's binary cross entropy on this, but this is not going to be easy to interpret. I think in here, I think the 2D and 3D losses are more interesting.
So here's the higher the better, or the lower the better?
The lower the better, yes.
Do you have any other questions? No, then thank you once again.
Thank you.
Okay.